Okay, well, good afternoon, and thank you for the organisers for inviting me here. So what I'm going to talk today is about first principles exploration of dense materials, and we've been hearing nearly all day about what happens when you squeeze things a lot. What I'm going to try and focus on a little bit is what those might actually look like at an atomistic or microscopic scale. I'm going to suggest that computation and theory is a way of giving us sort of a preview of what they might look like eventually when we get the experimental techniques to do the crystallography or structural analysis at these high pressures. So first principles, from my perspective, means starting with quantum mechanics and working forwards to the answer. So there's not much empiricism in this. We're not trying to fit to any experimental results. We're trying to go to the basic laws of physics as we understand them and see what the consequences are. And the power of that is that we can move into regimes where we haven't got very good empirical data at all, and it allows us to make predictions. So this is my slide on condensed matter, and I think it nicely highlights the importance of the different bits of experimental apparatus for reaching different regimes and different pressure scales that might be encountered in the universe. So on the far left-hand side, we've got a large press that might be able to, this is macroscopic, about the size of a person, but can maybe squeeze centimeters of materials up to gigapascals of pressures. If you want to reach pressures somewhat similar to the center of the Earth, you have to move to these diamond anvil cells. This is for static compression. But to go further, we lose static compression. We have to appeal to the sort of dynamic compression that we might get from, for example, the National Ignition Facility or the Z-pinch machine, which will allow us to explore pressure regimes and temperature regimes that might be found, say, in Jupiter. But we can keep going, and pressure, there's no stop to pressure. You can keep squeezing and squeezing, and you can go to higher and higher pressures to the petapascals, and I don't even know what 10 to the 98 petapascals is, or what even the word for that is, but that was I think I probably picked this off Wikipedia somewhere for an estimate of the pressure that might be at the beginning of the Big Bang, some sort of scale of some sort of thing. But we can keep going. We're just pushing particles closer and closer together, and we want to try and see what they will do. Now, these experiments are very difficult to do. We've been talking all day about how to do them. Once you've done them, it's very difficult to figure out what you've done, to find out where the atoms actually are in space. And this leaves a gap for people like myself to do some theoretical predictions of what might happen. So this topic is known as structure prediction. You can imagine it has a lot of applications to material science generally. So in my group, we work a lot on new battery materials or superconductors and so on. But here I'm going to focus on what really was the killer application of this technique, first principle structure prediction, which was dense matter. It was an area where there was very little experimental data, and therefore it was rather easy to say something that people didn't know before. So the basic question is, what structure will a collection of atoms adopt? And we follow, essentially this is a kind of a global optimization. We're trying to lower the energy of arrangements of atoms. They might be in crystals or individual smaller arrangements. Mostly today I'll be talking about crystals, but structure also includes defects of different kinds, grain boundaries, interfaces, and so on. And the approach that I've been taking, and it's very similar to other approaches exist there, is using the power of computation that we have at our hands now. So we can easily get hold of multiple CPUs to do parallel computations along many different calculations all at the same time. This is something that's become possible over the last 20 years or so. We've also got computer codes that allow us to faithfully reproduce the quantum mechanical behavior of materials at that scale. And that's something I spend a lot of my time doing, is developing these so-called density functional theory electronic structure codes that are robust. And the key thing was the robustness of these codes, because when I started my PhD, you had to recompile the code for each new crystal we were going to do the calculation on. If we want to do multiple different crystals, you need the code to just work once and for all, and we're now in that state. So what we essentially do is build thousands of random crystals and then feed them into our density functional theory code, farm it out to a cluster, do a structural optimization, so move the atoms to their lowest energy configuration multiple times, and then collect the output and essentially rank the structures by energy, or in the case of pressure, enthalpy. And the very nice thing about pressure was the enthalpy is just a pressure times volume of the unit cell. That's really easy to calculate. So for me, The difficult bit is the internal energy, the U, that's all the quantum mechanical stuff, but there's no problem just turning that pressure knob up as high as I want to go. It just makes the unit cells smaller and smaller and smaller, pushes the atoms closer and closer together. Now I'm just going to briefly emphasize here, there was this, in the early days of structure prediction, so Richard Catlow was very involved in this from a chemistry point of view, and there was lots of discussion, and it was felt that because lots of calculations had to be done, the only way to do it was to use fast empirical model potentials. Okay? But it turned out this didn't really work very well, and here's an example showing why this didn't work very well. I've got a density of states of structures. So I've done lots and lots of structural optimizations, and I've looked at the energy of all the different structures that I'm getting, and I've plotted a histogram. And so you see a distribution, and the white distribution is the distribution we get when we do a quantum mechanical simulation. And you can see it looks nothing like the other coloured ones. The grey one particularly is a very famous potential for silicon called the Tursoff potential. It was carefully crafted to reproduce the properties of silicon when it's in its ground state, but didn't describe the silicon very well when it's in any other state at all. And so most of the structures you generate by exploring the landscape of possible structures are nonsense. Okay? These were these empirical potentials. But the DFT ones, they go, they take you down to a low energy rather quickly. Now, in fact, this has all been turned up on its head in the last 5 years with the resurgence of resurgence, I think is fair enough actually, the resurgence of machine learning. Where we're now using machine learning potentials to map out these energy landscapes and then speed up these searches. But the key thing was we need to map out the whole energy landscape, not just what's going on at the bottom of the energy landscape. So this is work we've been doing with Volker Derringer in Oxford and Gavel Channy in Cambridge. Many other groups are. Well, everyone's doing machine learning now, so we're all very busy in that area. Okay, so around 2004 or 5. I started doing this structure prediction, and Richard Needs in Cambridge asked me, can you do this for hydrogen? And I'd been trying to do carbon, I'd been trying to do material science, because that's where I sort of started out. And it was kind of hard work. So I said, hydrogen, that's easy. It's only got one electron per atom. So that's what got us going on applying these techniques to high pressure materials. So Richard had obviously worked in this field for a long time, seen the importance of doing high pressure simulations at high pressure. And so we used this random sampling technique to generate actually what are still the best models that we have for hydrogen at high pressure. So these pictures in the bottom left-hand side are the output of a paper we published together in Nature Physics in 2007. And these are for all of the sort of future theoretical studies and what experimental studies there are on the structure of hydrogen, they're using these crystal structures as the input to do various high-level calculations. We also found out that when we took ammonia and applied a megabar of pressure to it, it spontaneously became ammonium amide. Okay, this is really speaking to Stephanie's point that there's things happen that we just don't expect are going to happen when we apply things to high pressure. This was not anticipated, and so the first principles approach allowed us to discover this computationally. Now, indeed, as it was also pointed out, I think in the last talk, you can't trust theory completely, so you've got to go and do the experiments at some point, and these experiments have been done on the ammonium amide. These have been discovered experimentally subsequently. Now, the result that probably got me the notice of this field or this group was, as I said, pressure is just a number I need to put into my input file. And once I got going on this, I decided to see how far we could go. And playing around with aluminium, this simple metal aluminium, I found that at a few terapascals, it actually collapsed into a new state, a new phase, which is this complex host-guest phase, which was important because aluminium was a standard material that used for looking at shock experiments. So I think this is probably why I'm here, but we've gone on and done other things as well, which I'll show you in a couple of slides' time. Now, all of those examples I showed before were crystal structures for a single composition of materials and fairly small, simple structures. This was 10 or 15 years ago, the kind of calculations we were doing. Now in my group, we're doing different things. We're doing searches over whole ranges of compositions. So this is an example done with Andreas Herman in Edinburgh and Lewis Conway, who's now in my group in Cambridge, where we mapped out the chemistry, or essentially mapped out organic chemistry at 500 gigapascals. It's kind of a pressure relevant to the Uranus interior, and we found interesting things, in particular this stable quaternary compound, the hydrogen, carbon, nitrogen, oxygen compound, which surprised us, but maybe shouldn't have done because it's isoelectronic with diamond. It's got exactly the same electronic structure as diamond. If you count up the electrons. And this is a predicted stable quaternary phase, not been found experimentally yet. But the key point is here, each of these dots, I mean, there's many dots not shown, there's many compositions we've explored which we've not highlighted, and each of those dots are the result of hundreds of thousands of structure searches, all done at once in parallel, on parallel computers. Okay, so now I want to just talk about what does matter look like if you keep squeezing it, and I take it as an example carbon, because carbon's very interesting. It's already got lots of structures under normal conditions, from buckyballs, diamond, graphite, graphene, lonsdaleite, nanotubes, all very exciting materials and quite different. You might ask the question, if you're in this community, what happens if you squeeze diamond and keep squeezing it? Now we know something must happen, because the diamond structure is an open structure. There's lots of space in it. So if you squeeze it, the PV term in the enthalpy is going to highly penalize your structures. So I have been tormented over the years by pictures like this that appear on BBC websites. There's this claim of there being diamonds in the center of big planets or stars, and this artist's impression of a beautiful cut diamond. I don't know how anyone managed to get a cut diamond in the center of a planet. But obviously this can't be true. At very high pressures, the space in diamond is going to be squeezed out. We've seen pictures like this today as well. The capsules in the National Ignition Facility, these are made out of high carbon content materials. So it's actually relevant to find out what might happen to carbon when you squeeze it. So here's the result of some work I did with Miguel Martinez, and he was a postdoc of mine at UCL at the time, and the outcome of this work was me convincing him not to keep increasing the pressure by, say, 10 gigapascals at a time, but by keep multiplying by 10. To work logarithmically with the pressure. Keep going, I said to him. And in doing so, he actually found 4 new thermodynamically stable phases of carbon at high pressure. Predicted, not found experimentally yet. We start at graphite, we squeeze and it becomes diamond. The BC8 structure has been long theorized to be a high pressure phase of carbon, as has simple cubic, but we found then simple hexagonal, an FCC structure that I'll come back to in a second, a double HCP structure, and finally the BCC structure. Now, the FCC structure is quite interesting. So this looks like it's gone back to being, it's a close packed structure, but actually when you analyze the electronic structure, it's something known as an electride. The electrons have just gone off and done their own thing and become anions and their own crystal structure. So this is actually the calcium fluoride structure, okay, where the fluorine is, where these green blobs, which are blobs of electrolytic charge, are playing the role of the fluorine in this structure. So that's actually the reason why aluminium becomes complicated, because it actually becomes a binary compound. It becomes this electride as well. So this is another of these kind of unexpected things that happen when you squeeze material to higher pressure. Another example, what happens if you start mixing elements together and applying pressure to them? What happens if you mix iron and helium? Now helium, famously unreactive. Okay? But we find when we apply a few gigapascals of pressure to it, it reacts with iron. It reacts with iron and it's exothermic reaction. And the phase diagram here, it may not be perfect, but we've predicted roughly the phase diagram, and we find it stable solid phase up to tens of thousands of Kelvin. Okay, I know from this crowd tens of thousands of Kelvin is low temperature, but for us it's pretty hot. We also predict that there's a superionic phase where the helium starts zooming around and doing their own thing in the lattice as well. So not only do the electrons do strange things, chemistry just doesn't behave the way that you would expect it to if you went to a chemistry department and asked them how things work. So we're entering a new regime at these high pressures. Now, the one curious thing is we actually do know what the ultimate fate under pressure of all elements are. So as you squeeze and squeeze and squeeze an element, eventually all the electrons get squeezed out of the atomic orbitals into a uniform electron cloud. And so you just have point positive charges in a uniform electron background. There's an electrostatic solution to that, which is the BCC lattice. So the prediction is, at high enough pressure, everything becomes BCC. An example here is a movie of actually a single random structure search for hydrogen at extremely high pressures. And as you follow it, relaxing down, it's going downhill all the time. This is a longer talk. I can explain why random structure search works, but here you can see it working. This crystal structure. I only ever did one random sample for this example, and it pops out and it looks like perfect BCC hydrogen. Actually, if you look in more detail, it's probably can't see from where you are, but there's something a bit funny going on in this structure. There are actually dislocations in this structure. So even if everything becomes BCC at high pressure, there's still all the microstructure of BCC to explore. In fact, I come from a material science department where a good chunk of the department is focused entirely on a BCC structure, iron, okay? And they have their whole research lives laid out because of all the defects that you could put into the doping, the steels that you could make from it. So even a simple BCC lattice is likely to be complex. However, this ultimate phase of matter is likely to occur at extremely high pressures. If you think of a uranium atom, you're going to have to apply extremely high pressures, way beyond the petapascals, to get the 1s electron of a uranium atom out into the uniform electron gas. So there's this huge range from where we've done calculations up to so far to this ultimate limit. So my conclusions are the following, that we can use first principles to explore extremely dense matter. It doesn't mean they're necessarily precisely right, but they're giving us the right questions to ask. Is it this? The chemistry and compositions can be wildly different than what we expect under ambient conditions. And I point out that the penultimate fate of matter remains unknown. So we know the ultimate fate, but the role for the machines like the M4 is to help us figure out what happens before we reach that point. Okay, and that's the end of my talk.
Thank you, Chris. And do we have time for a couple of questions? Yeah, Aidan again.
Thanks, Jerry. Really interesting talk. My question is, since you're mapping out the whole of the energy space, can you find metastable states and work out about reaction kinetics? Because it's you're saying this is the ultimate fate, but you might not actually get the energy to get there.
Okay, so this is thermodynamics, and kinetics is another business. So one of the really nice things about the random search is that yes, we're taking every local minima as seriously as any other. So we do get all the metastable phases. What we don't get routinely are the paths between them. Okay? Now this is, I think, has been a long-standing problem, and someone always asks a question like that. It's a very good one. What we really want to do is be randomly exploring all the possible paths that are possible. But this is, if you think about it for a while, this is a very difficult problem to solve. A bit more optimistic now that we've moved into this sort of regime of machine learning potentials. They're allowing us to do larger scale, longer time scale simulations than we would have done before. And the beauty of it is we can make these potentials now for these extremely high pressures. We can make them bespoke, just using machine learning technology, rather than waiting for someone like Tursoff to come up with the potential. Okay? This is a kind of semi-automatic way of making potentials based on the DFT calculations.
Just a minute.
Yeah, so thanks, Chris. Wonderful work. So the last question was basically a question about rates, and we know that we're seeing in dynamic compression experiments, we know we see phase transitions at different places due to the kinetics. But the other reason why one would imagine seeing transitions and behavior at different places where you would predict is because of strength. So that's going to be an interaction between the number of defects you're seeing and how quickly they can move and so on. So how easy is it for you to take into account strength and what that might do, seeing perhaps that's linked, perhaps strength and kinetics are linked, but
so with the kind of simulations we've been doing, I mean, okay, so the number of atoms, say, to discover the diamond structure, you need 2 atoms in the unit cell. But if you only put 2 atoms in the unit cell, you're not going to get a grain or anything like that. So you need to go up, I mean, unfortunately, to much higher scales. You need to go to the million atom scale. Now, indeed, people are starting to do this. I mean, it is quite an exciting time for materials modelling at the moment. The machine learning potentials are really allowing people to go to a much larger scale. So I think at the Gordon Research Conference there was some work from the US, I think from Oak Ridge, where they showed billion atom carbon shock simulations. And I think that's exactly what they're looking for. But not in my simulations.
Okay, I have one last question. I haven't actually answered one. You talked about the various gamut of approaches to actually realising these states experimentally. Out of what you've shown, is most of that realisable at diamond and cell pressures, or do you really need impact-driven pressures? This diamond example here, 5 GPa to go from graphite to diamond. To get BC8, you need a terapascal, and maybe they can reach a terapascal in a diamond anvil cell.
But I mean, at some point, you're going to reach the limit of the strength of diamond itself, and it's going to be undergoing these transformations. So you need to go to this next, to the multiple terapascal. Absolutely, you need another. And it's hard to see how static. You know, well, it's hard to see how. Oh, Justin's got a.
But we've gone to 2 terapascal on this and done the fraction experiment,
Yeah.
so it didn't go to BCA.
Yes. Okay. This is the kinetics.
That is the
Yeah.
entropy barrier that you need on the way out.
Yeah.
Okay, I've probably used up all the free time we had. So should we thank Chris and all the other speakers one more time?
Right, I've got the awful task of trying to stimulate some discussion now amongst us. Principally, you know, what would the community want in terms of access to the M4 machine? What could we do with it? What are the enablers? Where's the buzz? Where's the excitement? So what we've done in preliminary thought for this session is to divvy it up into sort of 3 blocks, really. Useful applications and research benefits, diagnostic capabilities and functional requirements, and collaboration and community. And they're the things that we chose looking at some of the feedback we had when the questionnaire was sent to many of you. So is community access, I think, is one of the things we should be looking at. We had an interesting comment, I think, from Justin, that it's easier to work with Livermore than it is with AWE. So access is clearly a prickly topic, and we should explore that. So what I'm going to do is to invite questions. Firstly, about the applications and research benefits side of things. If we don't get anything from the audience, I'm going to pick on people, by the way, as well. Right, which of the applications discussed already do you think are most useful and why? So anybody got a favourite application that you've heard about today that you would really like to vote for and really push for? You've all got your own favourites, of course. Right at the back there, we got a favourite. Excellent.
Sorry, but personal hobby horse is the radiation science-based side of things, and that's kind of relevant to the machine design stuff that we've been talking about around the edges today. So I guess what Stephanie was talking about in particular is somewhere where there's a vast amount of sort of material to explore, and it's very driver limited. There's lots of work that could be done if there were more machines available to do the work.
Right. So one of the questions that I wanted to ask a victim in the audience is that some of you have access to Z already. Is that already meeting your requirements? And were there to be an M4 machine, that really would be something we absolutely desperately need because there's this unmet desire to do more. So in your sort of area, is that the kind of thing that you really want to push for? Had you access to the machine? Yeah? Yeah? Looking around at people. How about other areas? Yeah, Jerry.
So not speaking for too many other people in the room, but I think most of the people got into this field for their interest in fusion. And we're all very happy that there's an alternative approach to fusion being explored by First Light. By the same token, I've spent 30 years trying to think of different ways to do fusion on Z. And we know that there are many other approaches that, with a pulse-powered device, we could potentially explore. So one question I guess I have for First Light is, what is the appetite? If someone comes forward with a proposal to the academic access process, which is essentially a competitive fusion scheme to what you're trying to do, how would that be received?
Right. Go on in, Nick.
Well, I mean, I think we'd be open to talking about it. We've already been talking with Faha about testing some of his ideas on Machine 3, actually. So I think the kind of the first thing first is it needs to work. Fusion needs to work. There's no value in the company for our investors if it doesn't work. So having alternative ideas is a good thing. And if you've invented it, but then you come and test it on our facility, okay, well, we'll probably have some know-how, you'll probably have some know-how, but that's more valuable to us than knowing nothing. So I think, yeah, we're open to it. There's been a lot of debate internally about how much we're planning for testing alternative designs. And at the moment, the decision is that we're focusing just on the one-sided drive, because basically this is already one of the most difficult projects that's ever been undertaken. So let's not make it more complicated by having 2 really complicated objectives or n really complicated objectives. But I think our investors and board are very open to having alternative ideas and being able to test them. So if we can make a really strong case, then we can do that. The problem comes when we're adding engineering risk to allow us to test an alternative idea. That's where it gets difficult, because how much extra engineering risk are we going to incur to test a backup idea, if that makes sense? So that's where the tension kind of comes. And this is where the kind of short pulse, long pulse machine tension comes, because that's a more risky, harder to build machine.
So that's the origin for my question, is obviously there are plenty of ideas that have been proposed previously that have not been tried at scale. Some of them on San Diego, very active programs in radiation-driven approaches, and what Dan was saying earlier, they could never get above 900 electron volts, and it was seen as too competitive to live. But for example, you could do revolver or a wire array using driven X-ray source. It would be additional risk, but it would be very much different to what we're trying to do. But maybe it's valuable from a de-risking strategy to try some of these things out to an academic access.
Yeah, and I'll just repeat the same thing and say I think we're open to that. So, I mean, you asked before about liner implosions, or how I interpreted your question. And I said there's a big difference between a short pulse machine and a long pulse machine in terms of performance. However, the long pulse machine which we presented would still be the best liner fusion machine in the world anyway. So it would still be extremely high performing, although not necessarily ignition. But, so yeah, we're open to it basically.
One of the things that I was going to prompt people on is how about applications that we didn't hear about today, which potentially could be explored with the machine? The only one that we had a sort of glimpse of that was snatched away from us was